Hey everybody, so this is the solution video for Worksheet 2.1. We're going to be talking about linear functions. And the first problem, we're asked to consider a line with a given slope of 3 and that the point 3, -1 happens to be on that line. So first we're asked to find the point slope form of the equation of this line. So let's kind of remind ourselves of what point slope form is. So given some slope m, which we are given, in this case it's 3, and some point on the line, and let's just call this x sub 1, y sub 1. So that's the point that we know happens to be on the line, or the line goes through at least. So given this, the point slope form is going to look like this: y minus the y-coordinate of the known point is equal to the slope m times x minus the known x-coordinate of the point that it goes through. So luckily we've got all of this. We've got the slope, we've got a known point right here, so all we have to do is just sort of put it together. So this 3 is going to be our x sub 1, and -1 is going to be our y sub 1, and we can just sort of put this all together. Okay, so we know that we're going to have y minus our y sub 1, which is -1, is equal to the slope 3 times x minus our x-coordinate, which is 3. We could clean this up a little bit, and this would give us y plus 1 is equal to 3 times x minus 3. And that's point slope form, so we just don't need to take it any further than that, but it's a nice easy way to take a given point in the slope and come up with a version of equation of a straight line. Now another way we can do this is to use what's called slope-intercept form, and that's what we're talking about here in part B. So with slope-intercept form, it's a little bit different. This is probably the most common one we're used to seeing, and this is given some point y, it's going to be equal to the slope m times the x-coordinate plus some value b, where m is the slope and b is our y-intercept. Thus, slope-intercept form, as opposed to point and slope form. Okay, so let's go ahead and see what we can do here. So we've got the slope already. We know that the slope is 3. So given that m is equal to 3, we can start to put it together. This is one way. There are other ways of doing this, but if we wanted to, we could say, well, y is going to be equal to 3 times x plus b, and now we need to get b. So to find b, we plug in a known point, xy. So we know from the previous, or from the directions, that 3, -1 is a point. So we're going to go ahead and do that. So in this case, we're going to use the point 3 minus 1. So our y is -1, our slope is 3, the x-coordinate is 3, and then our b is what we're looking for. So now we can sort of flesh this out, and we've got -1 is equal to 9 plus b. If we subtract 9 from both sides, we're going to conclude that b is equal to -10. So now we've got all that we need to get the slope-intercept form. We've got the slope, which is 3. We've got the intercept, which is -10. And we've got y is equal to 3x minus 10. So that's one way we could do it. Honestly, another way you could have gone about doing this is taken your point slope form that you already had and just gone ahead and multiplied that out and isolated y. Might have been a little bit easier, but I think it's good to see the strategy for the slope-intercept form. Okay, so now we'll move on to number 2. So here we're not given the slope, we're just given that a line passes through two given points, 3, -5, and 7, 4. So the first thing that we're asked is to go ahead and find the slope of this line. Well, let's recall that we've defined slope a number of ways. Change in y over change in x, rise over run. But if we wanted to think about it in terms of 2 points, we could think about it as the difference between 2 y coordinates divided by the difference between the corresponding x coordinates. So let's go ahead and name these 2 points. I'm going to call P point 1 and Q point 2. So if we wanted to find the slope m, we're going to take y sub 2, which is going to be 4, and we're going to subtract y sub 1, the y coordinate of our first point, which is -5, and watch your negatives on problems like these. Then we're going to take x sub 2, which is 7, because that's the x coordinate of point 2, and then 3 is our x sub 1. And when we clean this up, we're going to have, 9 up top, and then 4 in the bottom. So this would be the slope of our line, 9/4. Now, armed with this, in part B, we're asked to find the slope-intercept form of the equation of the line. And this is why it was helpful to talk about this method for slope-intercept form in the previous problem. So we know that m is equal to 9/4, and we also know, well, let's just kind of go from here. So from this we can conclude that y has to be equal to 9/4 x plus b. So again, we're in the situation where we need to find b, so we find b by plugging in a known point. A little redundant. Find b by plugging in a known point. And we've actually got 2 known points on the line. If you remember from up here, we've got 3, -5, and 7, 4. I'm just going to pick, for no better reason, I'm going to use the point 3, -5. Okay, so if we do this, we're going to say that -5, the y coordinate of that known point, has to be equal to 9/4 times 3, the known x coordinate, plus b. And now we've just got a little bit of arithmetic to work through here. So we've got, this implies that -5 is going to be equal to 27/4 plus b. We want to isolate b, so let's subtract the 27/4 from both sides, and that's going to give us -5 minus 27/4 is equal to b. Okay, so let's get a common denominator here. So -5 can be expressed as -20/4 minus 27/4, and this has to be equal to b. So we'll see that b is going to be equal to -47/4. So we've got our m, we've got our b, so here's our big so. Now we can conclude that our y is going to be equal to 9/4 x minus 47/4, and that's going to be our slope-intercept form for this line. So that should do it for that problem. So now if we move on to number 3, we're asked to graph the following linear function, and this shouldn't be too difficult given what we've done already with graphing functions. So specifically, we're asked to first find the slope, y-intercept, and x-intercept to get a good idea of what this line's going to look like. So let's go through and see what we've got. Well, we know, given this linear function, we know a few things of it already because it's in slope-intercept form. So we know that m is going to be equal to 2. That's this number right here. We also know that b is equal to -1, so that's our y-intercept. So in terms of things that we know already, the slope is equal to 2. Our y-intercept is going to be equal to -1. And by the way, we also talked about the y-intercept always being f of 0. if we did evaluate this function at 0, we would still get that as our y-intercept. The last piece that we need is the x-intercept. And for the x-intercept, if you remember, what we did is we went ahead and we took our function f of x, we set it equal to 0, and then solved for x. So we're going to go ahead and we're going to do that now. So we'll take our function, which is 2x minus 1. We're going to set it equal to 0. And first we'll add 1 to both sides. So we'll get 2x is equal to 1. We'll divide both sides by 2. And we get x is equal to 1/2. So there's our x-intercept. So if we wanted to go ahead and graph this now, we've got more than enough information to get a good graph together for this line. So we'll draw our axes. So this is x, and this is y equals f of x. And we'll go ahead and we'll plot some points here. So here's -1, -2, 1, 2. And that should do it. So the points that we know as the y-intercept is -1, so we can plop that right there. And we know our x-intercept is 1/2, so we can put that right there. And those two lines, or those 2 points, are enough for us to draw a line to represent our function. So we've got the proper x-intercept, the proper y-intercept, and this function is y equals 2x minus 1. So that wasn't too bad. Now let's move on to an application problem here. So we're given the unemployment rate for 2 different years, starting in January of 08 and then again in January of 09. And we're asked to find a linear function that fits these 2 data points using the number of years since January of 2008 as t as the independent variable and the unemployment rate u as our dependent variable. So in essence, the t is going to sort of be our x, or our input, and the u, we can think of this as, this is our y, this is our dependent variable, or our output function of the function. So let's go ahead and see what we can do here. I'm going to go ahead and sort of write these as 2 different points. So if the unemployment rate is our u, let's say this is our point 1 and this is our point 2. Those are the 2 data points we're working with. So this 5% will represent I'm going to call it u sub 1, but the unemployment rate for our point 1. And the year 2008 means that the time, or t sub 1, is going to be years since 2008 will be 0. So u sub 1 is 5, t sub 1 is 0. And then here, this will be our u sub 2, and this year will represent our t sub 2. U sub 2 will be 7.7, and t sub 2, January 2009, is 1 year that has passed since 2008. So we should have our 2 data points now. Okay, so given those 2 points, what we want is we want a linear function for this. So maybe it's going to look something like this. U is equal to m times t plus b. So this is just a slightly different version of slope-intercept form, except instead of x's and y's, we have u's and t's. So, but it's still the same process. The first thing that we need is the slope. So to find m, this is going to be the difference in our dependent variable divided by the difference between our independent variable. So just like our x's and y's. So using the points that we lined up top, we've got 7.7 as our u sub 2, minus 5 as our u sub 1, and then we've got t sub 2 is 1, t sub 1 is 0. So this is going to give us 2.7 divided by 1, or just 2.7. So there's our slope. So at this point, we've got u is equal to 2.7 times t plus b. And you may already see what b is, but just in case, let's use our technique for finding b as we pick a known point. And in this case, our point will be some point t u. And let's pick the point t equals 0, u equals 5. If we use that point, we're going to have 5 is equal to 2.7 times 0 plus b. This is going to give us 5 is equal to 0 plus b, so we get b is equal to 5. Now you probably were able to recognize that our slope or our y-intercept was going to be 5 because of this point. This is what the coordinates of a y-intercept looks like. X is equal to 0, y is equal to 5. So maybe we didn't need to do that, but it's good to see it nonetheless. Now we've got all the information, so we know that our function is going to be u is equal to 2.7 times t plus 5, and that's the linear function that represents this data that they were giving us. Okay, so now we're going to actually use this to, assuming that this is a trustworthy model, use it to predict the unemployment rate for the following year in 2010. Well, the fact that we're given January of 2010, this implies that the year, or the t, is going to be, remember that it was defined as the number of years since 2008, so t is going to be equal to 2, and we just use our model, so u is going to be equal to 2.7 times our t value of 2 plus 5. That's going to give us, what, 5.4 plus 5, and that'll give us a grand total of 10.4. So that will be our unemployment rate the following year based on this data. And that seems to kind of make sense because it's growing linearly. So you know, in 2008 it was at 5. It grew 2.7 up to 7.7. It's going to grow another 2.7 points, or percentage points, up to 10.4 for this year. Okay, so that's our solution here. Now if we move on to the last question, we're asked to compute the average rate of change of a function over this specified interval. Now one thing to consider, and I'm going to abbreviate average rate of change as just ARC, just to save digital ink here. So in general, average rate of change, we can think of this as slope, and we define it as such. So if we ever wanted to find the average rate of change of a function over a specified interval, then it's just going to be the change in y values divided by the change in x values. We can define it again as given 2 points, the difference in the y coordinates divided by the difference in the x coordinates. Another way to think about it, remember, if y is equal to f of x, we could also think of average rate of change as f of x sub 2 minus f of x sub 1, since those are just y sub 2 and y sub 1 respectively, divided by x sub 2 minus x sub 1. So all perfectly legitimate ways of thinking about average rate of change. So now we've got to go ahead and use this formula to calculate this average rate of change here. So let's think about what we actually have. So given that this is our interval, we're trying to find the average rate of change between x equals 9 and x equals 16. We can go ahead and start labeling some things. I'm going to let my x sub 1 be 9. I'm going to let my x sub 2 be 16. So that's going to take care of the bottom half of this formula for average rate of change. Now we need to take care of the top. So if x sub 1 is equal to 9, then f of x sub 1 is just going to be f of 9. And that's going to be, our function is a square root function, so it's just the square root of 9, which would be 3. We can do the same thing for x sub 2. We take our function, we evaluate it at x sub 2, which is 16. Our function is the square root function, so that's going to give us 4. So these are basically our corresponding y values. If we'd rather think of it as our y sub 1 and our y sub 2, that's perfectly fine. All right, so let's use this information to now calculate the average rate of change. So average rate of change for us is going to be equal to our f of x sub 2, which is 4, minus our f of x sub 1, which is 3, divided by x sub 2, which is 16, and x sub 1, which is 9. And if we go ahead and calculate this out, we'll have 1 divided by 7, and that's our average rate of change. So we're really just using the slope formula to do this. We just have to set up our points. So having said that, I think it would be helpful to see what's going on graphically here and what this average rate of change really means, because this is really where we start to spring off into a lot of the ideas of the first half of calculus with average rate of change. So graphically, let's take a look at this. So I'm going to set up the axes, and this may not be scaled perfectly, but you'll get the idea. So this is our x, y is equal to the square root of x. We know that the square root function kind of looks something like this-ish. And we can just go ahead and pick our points. So let's say that this is 9 and this is 16. And we know that this is going to be 3, and this point up here is going to be 4. So again, not perfectly to scale, but you get the idea. Okay, so we know that these are the 2 points that we calculated. And what we're trying to do is we're trying to find the average rate of change over this interval. And the way that we did it is we essentially found the slope of a line, a straight line that would connect these 2 known points. We call this a secant line. So if we were to look at this line, the slope of it would be the 1/7 that we found. So, you know, the slope maybe here is maybe a little bit more than 1/7. The slope or the rate of change of this graph at 16 is maybe a little less than 1/7. But on average, over this interval, the average rate of change or the average slope is equal to 1/7. Okay, so that does it for the 2.1 solutions, and I'll see you all in the next video.